Hi everyone, I hope you are all doing well. I am sorry that it seems that we will not meet again the rest of the school year. I'm super bummed about it. I miss all of you and I hope you're doing well. Trying not to stress too much and hopefully you're not working too much either. Alright, so we're going to go ahead and start with our 10.3 notes, and that is page 8 of the packet. So starting with these two things, which is our permutations and our combinations. I posted on Google Classroom the website that you can use for the calculator. Also on the calculators, you should have if you have a scientific calculator, you should have a probability button. Mine is right there, and I hit that, and then I select which one I need. So if it's permutations, I use number 1. If it's combinations, I use number 2. So, for instance, if I had, let's say, 5 permutation 3, I would go ahead and instead of having to use this formula and everything else, if I use the formula, it would be 5 factorial over 5 minus 3 factorial, because this is your n and this is your r. So instead of doing 5 factorial over 2 factorial and having to work it all out, I can just do it in my calculator, and I first type in 5, and then I go to my probability button, and I hit the permutation one, so I'm just going to hit enter on that, and then I hit 3, and I hit equals, and I can see that it's 60. So instead of having to do all the math, I can just type it in the calculator. Alright, so this is how you will see the setup for those as NPR. Alright, after that, you guys are going to make sure that you understand what permutations are. Permutations are arrangements of n distinct things taken r at a time. So, for instance, when we look at how people are seated, we care about how they are arranged. We care about the order of them. So, with how things are seated, or even like the order of houses, or the way that people win a prize, first, second, and third place. Those would be permutations. So repetitions are not allowed in permutations, and the order does matter. Okay? So permutations, the order matters, and repetitions are not allowed. For combinations, you're going to do the same kind of thing here, except your formula is a little bit different. Combinations are subsets of n distinct items taken r at a time. So, with combinations, repetitions are still not allowed, but the order is not important. So, for instance, if I'm making a committee or a group of people, I'm going to have the same members of my committee. If I have members A, B, C, I'm going to have that same member group if I have BCA. It's still the same group of people. Whereas if I'm looking at things like for permutations, the order of things coming in a certain place, if we have first, second, and third place, it's going to mean something different to have ABC than BCA. Those are two different things. Whereas in this case, they're the same. You still have the same grouping. Okay. With combinations, you can also use your calculator. And something you can do to find combinations and permutations on your calculator for how to do that, just type in on Google combinations and permutations, and then just type in the type of calculator you have. So for me, let's say I want to do 5 combination 3. If I were to use my formula, that would be 5 factorial, because that's your n and that's your r, over 3 factorial times 5 minus 3 factorial. So this is 5 factorial over 3 factorial, 2 factorial. And instead of doing all of that, you can just use your calculator or the website I sent out, and you can type in 5 combination 3, and you would have 10. Combinations will almost always be less options or less ways of doing it than permutations because the order doesn't matter. So these would count as the same thing. All right. You also have from section 10.2 your fundamental counting principle, which is when you just multiply out the different options. So for this example, if you selected items that can be repeated, for example, how many 4-digit numbers are there? So you have 4 digits for a number. 0 through 9 work. So for each of these digits, the ones place, the tens place, and the hundreds place, there are 10 options, 0 through 9. Now, you can't use 0 here because if you use 0 here, it would just be a 3-digit number. So you can only use the digits 1 through 9 there. So there are 9 options there. So that's why for this one it would be 9 times 10 times 10 times 10, which is 9,000. So that is the fundamental counting principle. We can't use a permutation or combination in this one because repetitions are allowed. So it can be repeated, so we use the fundamental counting principle. All right. If items cannot be repeated and the order is important, we use permutations. So how many ways can 3 people line up at a ticket counter? You would have 8 permutation 3, so that's 8p3. And so I have 8 times 7 times 6, or you could just type it in your calculator as 8 permutation 3, and you get 336. For this one, and you could also do this one as 8 factorial over 8 minus 3 factorial, or 8 factorial over 5 factorial, and it'll give you that same answer. If the selected items cannot be repeated and order is not important, use combinations. So as an example, how many ways can a committee of 3 people be selected from a group of 12? You would have 12 combination 3 because the order does not matter. Okay. There is a table on the next page that will help you understand permutations and combinations. Both of them use R and N. So N comes first, R comes second. So this for permutations would be NPR. And for combinations, NCR. In both of them, repetition is not allowed. With permutations, order is important, but with combinations, it is not. Clue words to help you distinguish which one to use. For permutations, clue words would be arrangement, schedule, or order. Clue words for combination would be set, group, sample, or selection. Okay, so we're going to look at some examples and we're going to decide here which of these are going to be permutations or combinations. Or it can be our fundamental counting principle. And I will abbreviate that with FCP. And this is also from 10.2. So they can be permutations, combinations, or the fundamental counting principle. Fundamental counting principle is going to be used if repeats. If numbers repeat, we're going to use that one. These ones are like homework problems 42, and 43. All right, so a telephone number. If you think of a telephone number, first question that you want to ask with these ones are there repeats? That's the first question. If there are repeats, so let me actually make kind of a little bit of a tree. If repeats are allowed, if your answer to that is yes, then that is the fundamental counting principle. If repeats are not allowed, then you're going to ask the question, does order matter? If order matters, if your answer to that is yes, you're going to use permutations. If your answer to that is no, then you're going to use combinations. Okay, so for this one, does a phone number allow repeats? Yeah. When I think of my childhood phone number, the first 3 digits were 577. So, repeats allowed. So this one automatically is going to be our fundamental counting principle. So, a social security number. I have even repeats in my social security number. Repeats are allowed. So, it has repeats. So this one will automatically be fundamental counting principle. A hand of cards in poker. If you have a hand of cards in poker, each card is distinct. You have your ace of spades, you have your ace of diamonds, and then you have all of the other 52 possibilities. So you're not going to have repeats. So this is no repeats. And if we think about our hand in poker, it does not matter which cards we get first. If I am given a 2, 3, 4, and 5, it's not going to matter if I get a 5, 4, 2, and 3. It's going to still be that same hand. So, order does not matter. So because of that, I'm going to be using combinations. For letter D, a committee of politicians. So, if I have a committee of people, the first thing I want to do is think, are repetitions allowed? We can't use the same person twice, so this is no repeats. And the next question I'm going to ask myself, does order matter? If I choose Bill and then Bob, it's the same group as if I chose Bob and then Bill. So, order does not matter. So I'm going to use combinations. A combination on a combination lock. So this one's a little bit of like a misleading sound. If you think of a combo for your lock, you are going to have sometimes it repeat. So repeats allowed. So this one is going to be our fundamental counting principle. Because your combination might be 10, 20, 10. Or it might be 10, or let me give a different one. It might be 13, 35, 13. That could be your combination, so repeats are allowed. A lottery choice of 6 numbers where the order does not matter. So when you pick your lotto numbers, you have usually like between the numbers 1 through 40 or maybe 1 through 60, and you're picking which balls will end up being chosen for the lottery. You're not ever going to have that same number used, so repeats are not allowed. No repeats. But with the lotto, it does not matter which order the balls were sucked up into the thing. So Order does not matter. So this again would be combination. And our last one. For this one, an automobile license plate number. You can have repeats. So this one would be fundamental counting principle. All right. Now, we will go through some that are permutations, so don't worry. These ones are like homework problems 24 through 27. This one says, Jeff Hubbard, a contractor, builds homes of 8 different models and presently has 5 lots to build on. In how many different ways can he arrange homes on these lots? Assume 5 different models will be built. Okay, so we have 5 different types of models that are going to be used. So we have no repeats. And the other thing with this one is we have arranging of the homes. So he cares if model 1 is used first, or let me use letters. If he has models A through E that he ends up picking, it's going to make a difference if we have A, B, C, D, E in that order as A, C, D, E, B. That's going to look different on the block as opposed to that. So, the way that he arranges them, order matters. So, we're going to be using permutations. So, I have my N and my R for permutations. This is how many different possibilities there are of selecting from. There are 8 different models to choose from, and I am actually selecting 5 of those. So this is going to be 8 permutation 5. So to get that in the calculator, I have 8 permutation 5. That is 6,720 different ways. For number 3, how many ways can a teacher give 5 different prizes to 5 of her students? So she has different prizes, so there are no repeats. And because the prizes are different, the order matters. If the first prize is stickers, that's going to look different to a certain student than it would be a gift card. So the order matters and there are no repeats. So this again is permutations. So for this one, my N, the total options that I have to choose from, would be which of the 25 students get prizes, and I know that 5 of them will. So 25P5 is going to be, and it's a big number, 6,375,600. If you did this one using the fundamental counting principle, you could technically do that. When you think of the fact that you have 25 different prizes, the first prize has 25 options of students, and then 24, and then 23, and then 22, and then 21. So because of that, you could just multiply those 5 numbers and you would still get that same answer, 25 times 24 times 23 times 22 times 21 is the same answer. Okay, in the next question, it says, how many 5-member committees could be formed from the 100 U.S. senators? So, this is a group, and each member is equal. There is no difference between the first member picked and the second member picked. They're all still part of that same committee. So, no repeats, because they're distinct people, and order does not matter. So because the order does not matter, we're going to be using combinations. So I have 100 to pick from, and I have 5 that will actually be chosen. So 100 combination 5 would be 75,287,520 ways. Okay. The next page is going to be going over some different ways in which you can choose cards. So this one is how you guys will choose cards. Before we do that, I want to have us look at what is actually in a deck of cards. So in a deck of cards, the deck that is being described by the name a standard deck is also known as a French deck. The name points to the deck's origins and history. There are a number of important features to be pointed out for this type of deck. The main items that are necessary to know for probability problems are the following. There are a total of 52 cards in every deck. So you have 52 cards in every deck. There are 13 ranks of cards. The rank can be anything from 2 all the way up to 10, and then a jack, queen, king, or ace. So those are your ranks. The ace is technically your highest. So it goes 2 through 10, jack, queen, and ace. In some situations, ace ranks above king. In other ones, it can be thought of as low. It doesn't matter for these questions, so you'll be fine without knowing that. There are 4 suits. So each of the cards, 2 through 10, jack, queen, king, and ace, they can have a different suit. They can either have, and that's the kind of symbol that goes along, spade, heart, diamond, club. Those are the different suits. So you have 4 different suits, and there are 13 cards in each suit because you have a 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, or king, or ace. The diamonds and hearts are printed in red, so you will have 26 red cards and 26 black cards because you have 13 here and 13 here. Those are both black cards, and you have 13 here and 13 here, and those are both red cards. Each rank has 4 cards in it because you have 4 suits, so there are 4 10s, 4 9s, blah, blah, blah. The jack, queens, and kings are considered face cards. So these ones right here are your face cards. And there are a total of 12 face cards. And we don't deal with jokers. So jokers are not anything that we do have to worry about. Okay, I'm going to skip this part right here and go straight to the bottom. We want to find out how many there are of these. So we're not doing combinations or permutations yet. We're not counting yet in terms of that kind of math. What we're going to start with is just how many of those types of cards exist in a deck. So, how many black cards are there? Well, we have 13 spades plus our 13 clubs, so that would be 26 cards. For number 2, how many aces do we have? Well, we have a spade, heart, diamond, and club. So there are 4 aces. Picture cards. We have 4 jacks, plus 4 queens, plus 4 kings. So we have 12. Queen of hearts. So how many queens do we have? Well, we have 4 queens, but how many are of the symbol heart? That would only be 1 specifically. Kings, there are 4 kings. Clubs, well, we have 13 of each symbol or suit, so there are 13. Not spades, so that would be 13 diamonds plus 13 clubs plus 13 hearts. So together that would be 39. Red cards, that would be 13 diamonds plus 13 hearts. So that's 26. Tens, there are 4 of each rank. Red jacks, well, we are going to have a red, we're going to have a jack that's a diamond, and we're going to have a jack that's a heart. So that would be 2. Black threes, we're going to have a 3 that is a spade and a 3 that is a club. So that would be 2 cards. Red nines, a 9 that's a diamond and a 9 that is a heart. So that's 2. Number cards greater than 6. We would have 4 sevens plus 4 eights plus 4 nines plus 4 tens. So that would be a total of 16. And then red picture cards. We are going to have 2 jacks plus 2 queens plus 2 kings. So that would be 6. Okay. Number 5. This is our last problem from our notes. A standard 52 card deck contains 4 aces, 12 face cards, 13 hearts, 13 diamonds, 13 spades, and 13 clubs. If you have a 5-card hand, there are over 2 million possibilities for how you could get your hand. Now, if you are using cards, you are going to be using combinations. So, cards means combinations because we do not care which order we get them. And also to help you guys, this one is like homework number 28. Okay, so only cards of a single suit. If you have only cards of a single suit, think about the fact that you're going to have your first card. How many options do you have with your first card? Your first card will determine the suit, but you have 52 cards to choose from, and you will end up picking one. So that will be your first card. Now when you get your second card, your second through your 5th one, that is going to be determined by making sure that it is in the same suit. So 13 are in every suit. So because of that, you are going to have 12 left. If you already took your first card, that means that that's 1 card gone out of that suit. Let's say we have hearts. So now there are 12 cards left. And because you are picking 4 more cards, it's going to be 12 combination 4. So for this one, you are going to have 52 combination 1. We're first going to find what that is. Whoops. That would be 52. Next, we're going to calculate 12 combination 4. Which is 495. And you're going to multiply those to find the number of possibilities. So 52 times 495 is 25,740 ways. Okay, all red cards. Again, with this one, you are going to first think of how many red cards exist. So we have 26 red cards. So you're going to have 26 combination 5. With this one, we didn't have any restrictions on the first card. With this one, we do have restrictions on the first card. The first card and every other card following has to be red. There's 26, and we're going to be choosing 5 of them. So that's all that we have to do for this one. 26 combination 5. And we get 65,780 ways. For letter C, 4 aces and any other card. So for this one, you want to have 4 aces as the first thing that you do. So there are 4 aces, so you're going to be picking 4 of the 4. So you are going to have 4 combination 4 for that part. Now your last card that you choose, you know that you're going to be taking 1 card, but how many do you have left in the deck? Well, you have 52 to start with, but you already picked 4. So now you have 48 left. So 4 combination 4 is just 1. 48 combination 1 is just 48. So 1 times 48 is 48. So there are 48 ways to do that. Okay. We are going to skip 6 and 7 and even number 8. So that ends our 10.3 notes. I'm going to have us look at some of the homework problems from that section. So jump to your homework packet, and we're going to start with number 20. Alright, so with this, you technically just need to put it in your calculator. I showed you at the beginning of the worksheet what to do if you actually want to use the formula and everything, but really all you have to do is put it in your calculator. So I'm going to have 8 permutation 2. So with that one, I just get 56, and that is all you have to do. All right. The next one, number 21. We're going to do the same kind of thing, except I'm going to use combinations. So 13 combination 2. I get 78, and that's all I have to do. For 22, it says, determine the number of permutations or arrangements possible of 6 things taken 3 at a time. So this is N, and this is R. So we're going to have 6 permutation 3. So 6 permutation 3 is 120. Find the number of combinations of taking 11 things, so that would be our N, 4 at a time. So that's the R. So 11 combination 4. So 11 combination 4, we get 330. For these other ones, you have to decide if you use combinations, permutations, or the fundamental counting principle. So are we using combinations, permutations, or the fundamental counting principle? Remember, if repeats are allowed, we are going to be using the fundamental counting principle. If repeats are not allowed, we are going to then ask ourselves, does order matter? If the answer to that is yes, then you're going to be using permutations. If the answer to that is no, then you're going to be using combinations. So, how many ways can a president, vice president, secretary, and treasurer be chosen from a committee of 7 people? So, we have distinct positions. So because we have distinct positions, the order matters. If I choose candidate A for president, that means that candidate B being chosen first would change the results of the pickings. Also, repeats can't be allowed. We can't have the same person be president and secretary. So, order, does that matter? Yes. And are repeats allowed? No. So we're going to be using permutations. So I'm going to have 7 people, and I'm going to be picking 1, 2, 3, 4. So 7 permutation 4 is 840. For number 25, remember the questions that we're going to be asking. Can we have repeats? And does order matter? In a race in which 8 automobiles are entered and there are no ties, in how many ways can the first 3 finishers come in a race? So we are thinking about first, second, and third place. So are repeats allowed? No, you can't have the same person in first and third place. And does order matter? So with this one, if I have CAB, that's going to be a different outcome as ABC. These are different, so the order does matter. So we are going to be using permutations. There are 8 automobiles I am taking from, and I am selecting 3. So 8 permutation 3 is 336. Number 26. To win a lotto in one state, one must correctly select 6 numbers from a collection of 54. So the numbers 1 through 54. The order in which the selection is made does not matter. So, order does not matter. How many ways can how many different selections are possible? So, other question that we want to ask, are repeats allowed? Well, you can't have the same number show up more than once for the lotto in one actual setting. So no repeats. And does order matter? It told us no. So we are going to be using combinations. There are 54 numbers to pick from, and we will be selecting 6. So 54 combination 6 is 25,827,165 ways. So that would be your answer for that one. Number 27. Television and radio stations use 4 call letters starting with W or K, such as WXYZ or KRLD. Assuming that no repetitions in the second or fourth letters, how many 4-letter sets are possible using either W or K and only the letters I to U? So, for this one, are repeats allowed? So no repetitions in the second through fourth letters. But that means that we can repeat the first letter. So yes. So because of this, I'm going to use my fundamental counting principle. So we have 4 different letters. These ones are going to be the letters I through U, and this one has to be either K or W. So how many options do we have for that first letter? 2. Now, for the other options, I through U, you have I, J, K, L, M, N, O, P, Q, R, S, T, and U. If we count how many letters there are 13 letters. So that first one that our options are I through U, which is our second letter, we have 13 options. Now we are not allowed to repeat letters here. So how many letters are left for this one? It would be 12. And for the next one, 11. So you're just going to do 2 times 13 times 12 times 11. And you get 3,432 ways. And just one other one we're going to go through. You guys can also do number 29 now from this chapter. So this is also 10.3 or this section. And you will also be able to do 42 and 43. But I'm just going to go over one more with you guys today. This is a card one, so this is similar to the last part of the notes that we had. We have 5 card hands from a 52 standard card deck. We want to figure out how many ways we can get the following cards. So for A, it says, how many ways are there to get 2 spades and 3 non-spades? All right, so 2 spades. When you go to pick your spades, remember with cards, you're always going to use combinations, all right? With cards, we use combinations. So, how many spades exist in the deck? There are 13. How many are you actually taking? That would be 2. How many ways are there to get 3 non-spades? So non-spades would be 13 hearts plus 13 clubs plus 13 diamonds. So there are 39 non-spades. And because you only pick spades in the beginning, there are still 39 left. And how many will you actually be taking? 3. So you're going to solve for 13 combination 2 to get 78, and then 39 combination 3. That would be 9,139. So we're going to multiply those together, and we get 712,842 ways. Okay, letter B. 5 card hands consisting of 4 face cards and 1 non-face card. So 4 face cards. How many face cards are there? Well, we have 4 jacks plus 4 queens plus 4 kings. So there are a total of 12, and you'll be taking 4 of them. Now, how many non-face cards do you have? Well, there's 52 cards in a deck. Take away the 12 that are face cards, so there are 40. And when the first things that you picked, you didn't take any of the non-face ones, so there are still all 40 there. And you are only picking 1. So, 12 combination 4 is 495. And 40 combination 1 is 40. So you're going to multiply those two together, and you get 19,800 ways. Part C. 5 card hands consisting of 3 red cards, 1 club, and 1 spade. So to get your 3 red cards, how many red cards are there? There are 13 hearts and there are 13 diamonds. So there are 26. So you're going to have 26 and you're going to be taking 3. Now this one is a little bit longer because your 4th card is going to be 1 club. There are 13 clubs and all of them are left because you only have picked red cards so far. So 13 combination 1. And how many spades are there? There are 13 because you've only picked red cards or clubs, no spades yet, and you're taking 1. So 26 combination 3 is 2,600. 13 combination 1. Oops. Is 13. And 13 combination 1 is 13. Multiply those 3 numbers together. We get 439,400 ways. Alrighty. If you guys have any questions, just let me know. Email me. Anything you need, I'm here for you guys. Also, I will be posting the other videos shortly. Take care. I hope you are all doing well. And I can't wait to hear from you. Send me an email. Let me know how you're doing.